Let me start a little bit with the motivation for the paper. In the last couple of decades, we've seen, I guess, a lot of big surprises. The U.S. financial crisis, no one expected one to happen in the U.S. It was locked up and safe. The sovereign debt crises in Europe, impossible. The way the Maastricht Treaty was written, it seemed like that would be not something that could happen. COVID, we've had some experience with infectious diseases, but very little. Ukraine, and that's something we hadn't expected, to have violence and war in Europe. And of course, the U.S. debt limit carries with it all kinds of exciting possibilities for the near future. But all of them have very little precedence. They're surprising in that sense. We can't look back and see from history what we might expect. Now, at the same time, the models that we use are rational expectations models. And, you know, in the period before the U.S. financial crisis, we had something called the Great Moderation, and it looked like, you know, everything, it seemed like ideal circumstances for something like rational expectations, where people have kind of an understanding of the environment that they're living in. When you have shocks without precedence happening, then it's harder to explain what the justification would be of using rational expectations. So what we're doing in this paper is we're asking the question, you know, what if people don't have rational expectations, and that they instead learn about the world as the data come in. Now, there's a huge fraction of the modern macro literature that's devoted exactly to this question: what will people do when the rational expectations conditions are satisfied? And there's a large literature actually on the learning approach. There's various approaches. One of them is learning. Actually, Morton's written an important paper in this thing. I'm not going to reference Morton ever, or hardly anyone else during this presentation, but we sure will in the write-up of the paper, because it's an important paper on this subject. So there's a million unprecedented events without precedence that we could potentially study. We're going to go to the workhorse scenario for this kind of thing, which is the falling into the zero lower bound in 2009. And we're going to use the Egerton-Woodford kind of environment to think about the zero lower bound, and we're going to accept their obvious, from the point of view of reality, way oversimplifying, but we're going to be using their interpretation as it was an infectious increased desire to save. The questions that we ask are, number one, in the nonlinear version of the Egerton and Woodford model, it's well known that there are actually multiple rational expectations equilibria, both in and out of the zero lower bound. And one of the questions we ask is, does learning help select an answer, select one of the rational expectations equilibria? Now, this is a fairly well understood kind of area. I'll have some things to say about it, but I'm not going to elaborate too much on it, because that's not really the novelty here. So the answer is, does it select one of the equilibria? Yes, it does. Learning does select an equilibrium. The important question, or unimportant question, and which is going to be the focus of my presentation here, is the convergence to rational expectations equilibrium fast enough to justify using rational expectations as a kind of as a shorthand? And the answer we give to that question is no. Now, this is a preliminary. So far in our work, and maybe somebody will suggest something that maybe we should say yes. No, Marty says no. No. So anyway, our finding is the answer is no. And in particular, where our conclusion is that convergence is in fact extremely slow. And it's so slow that rational expectations is not a very useful guide at all for thinking about policy in the zero lower bound. Relationship to the literature, as I already advertised, I'm not putting any literature down here. What we're doing here is we're studying a nonlinear model. We're studying the global stability of the model. But what I mean by global is not that we have theorems about global convergence, but rather we have numerical experiments, and you know, we know that we know something about what happens there. So this is what we're going to do. Okay, the outline is, first I'm going to tell you about the model. Yeah.
So, I mean, this may come up or it may be completely irrelevant, but the thing about the new Keynesian model, the Egerton-Woodford model, is that, I mean, there's no endogenous state variables in it. There's no predetermined variables. Everything we're looking. So I wonder, is that important for this non-convergence result?
Well, I'm going to hopefully when I'm done, the reason for the non-convergence will be extremely clear. And but raise your question again, you know, maybe, but it doesn't, I'm never going to refer to the absence. Well, there is in fact an important state variable in our model because of the learning, but there are no state variables like the kind you have in mind. I'm never going to think about endogenous state variables, and so that makes me want to say that what we're saying is robust to, you know, but of course it'd be interesting to find out. Now, you'll see in a minute that the way we go, it's hard, it's a little bit tough to find out. Okay, so I'm going to describe the model. Then I'm going to talk about the results. Again, we have two types of results. One is equilibrium selection, but I'm just going to say them really fast. We can actually talk about stability in a way that I think is kind of interesting and maybe surprising in some way. And then, but the key thing is that we're going to have the very slow convergence to rational expectation. We would, by the way, are always going to have convergence to rational expectations equilibrium. The issue is it slow? Now, the results I'm going to present are a little bit shocking, at least to me. So it's going to be important to have, but for you to reproduce our calculations is not easy. So it's very useful. I'm going to show you a simple example where you can reproduce the calculations this evening as quickly in MATLAB. So in particular, I'm going to use a simple workhorse example at the end, if there's time. Okay, the model. So it's the Egerton-Woodford model. So it's a simple closed economy, new Keynesian model without capital, flexible wages, and Rottenberg-style sticky prices. I always say to myself something that Sergio says, stinky. Okay. Anyway, so there we go. And then the vision that we have is that the economy is in a non-stochastic steady state. Been there for a long time. Never expected anything to happen. And then at period zero, all of a sudden, the economy is perturbed away from the unique steady state. The unique steady state with positive interest rate. Here's beta. This is 1 over 1 plus RH. This is the discount rate in normal times. I'll call it H. And up until period zero, this thing is in the steady state with that interest rate and that discount rate. Then in the morning of period zero, everyone wakes up thinking it was just going to continue like before. But in fact, what happens is that the discount rate drops from RH to RL. That's exactly the model of Egerton and Woodford. And I'm going to let people know a bunch of stuff, probably more than I should, but people are going to know the law of motion of the discount rate. It's a two-state Markov chain. RH is an absorbing state, and the transition probability of going from low to high is a constant P. Extremely convenient thing, which was convenient both for Egerton and Woodford and everybody else who's used this, and especially convenient for us because we're going to use a lot of recursive stuff in our analysis. Now, what people don't know in period zero is they don't know what's going to happen to the economy. They know that they want to save more. They know that, but they don't know how the economy is going to evolve over time. And they also don't know what the effect of government policies are. What they do is they learn about these things as the data come in. And this is the critical intuition is a stupid sentence here. The way the learning works is a kind of a circular aspect to it, which is they learn from the data, so that's the obvious part. But the part that makes convergence slow is that data is moved around by what they learn. When they think, their beliefs and their thoughts influence the data. And it happens in such a way that causes convergence to be slow. It could be fast, actually, with the circularity. I'll explain. But in the zero lower bound, it happens in a way that it's slow, that the learning is a slowly moving thing. We allow people to learn in two different ways. The main thing I'm going to talk about is Bayesian learning, and then I'm also going to talk about constant gain learning. It does make a little bit of a difference. The Bayesian learning gives the most shocking kind of results, but the constant gain learning gives us effectively similar results. So now I'm going to talk about the households. So here's the timing of a typical day for the households. So they wake up in the morning. Now, I should mention here, we have to have a bond market in this model.
And they're not in zero.
Bond market's going to clear at zero all the time.
Right.
But we must have a bond market in here because we cannot determine the interest rate otherwise. So, and the interest rate, of course, is an important variable. I suppose in the background you could imagine we have money in there separately, but it's the trade-off between money and bonds that the central bank plays with in order to determine the interest rate, and they have to. So you have to have a bond market. There has to be a trade-off between money and bonds. So we have to put in a bond market, although in equilibrium there will be zero, but this will be very important. So BH, they wake up in the morning and they see how many bonds they bought in the previous period. In equilibrium, they'll always see a zero. But in a second, they're going to make their choice, and then that's going to matter. So this BH is the bond. Just think of this as BH for an individual household. BH is the bonds acquired in the previous period. Little r is a discount rate for that period, and they observe it. In period zero, they observe the low value of that thing. Theta is a vector of parameters that determines their beliefs or characterizes their beliefs about x prime. Because we do Bayesian stuff, we're going to use, it's kind of convenient to use normal inverse Wishart parameters, so our distribution. So our theta has normal inverse Wishart has 4 parameters, so it's got 4 parameters times the number of variables that are in this vector x, which I'll talk about more in a second. What the household now has to do is form a state contingent plan. There's this x variable, and I'll talk about it more, but there's this vector x that they need to see in order for them to understand for their budget constraint to be well defined. So in particular, the choices people make, see, this H means it's for an individual person. This is employment. This is the bond holding, the saving for the next period. They have to make a plan. We're going to assume that they make a plan contingent upon of various variables, values for this variable X in the current period, which is aggregate consumption and aggregate inflation. Now this is going to look a little bit weird, so I'm going to focus. We're going to talk about this a little bit, and I'm pretty sure you'll get it. But right now it must look confusing. There's in other words, in their state, when they make their decision, this is the decision for these three things. It's the argmax over these three things of current utility plus continuation value. These are infinite live people, so the value corresponds to the value function, which is a function of the same variables on the right-hand side. They have a budget constraint, and the budget constraint involves a bunch of variables that are exogenous to the agents, in particular the interest rate, and that's going to be a function of the current value of little r and of this X thing. And this is inflation, that current inflation, so that's the price today compared to yesterday. And this is also a function of R and X. This is a function of R and X. And this thing here is taxes that they pay to taxes they pay to the government net of profits as a function of little R and X.
Expectation operator, like how do you define that?
So this expectation operator is the integral over all of these possible things using the density that's implied. Yeah, it's the Bayesian expectation, or whatever. They're using their prior, it's in their heads, it's not reality, I guess you could say. It's in their heads, that's based on their beliefs. Now, what I'm going to do is we're going to do a kind of a Walrasian type equilibrium. What I'm going to do now is I solve this for lots of different values of X. And then it's like getting a supply curve. You know, in order to get an equilibrium, you have to first get the supply curve. For this quantity, what price do you need? For that quantity, what price do you need? And so on. So I'm going to get all the quantities, lots of variable values of X, so that we'll do something in equilibrium in a few minutes with this thing. So what I have here is the decision about these three variables as a function of these things. And in particular, I'm thinking about X as I'm working out this decision for lots of different values of X. Here I just have a statement here about this X, which is this X here, but I've already emphasized that, is what allows me to uncover all of these different, it allows the household to uncover all these things. Now, there is one thing up here which I didn't explain more. Yes?
One quick question on the fact that the discount factor depends on R. Is it key for the loops that you mentioned at the very beginning, or is it simply for...
No, let's hold off. Let's hold off on the question about the loop that I mentioned at the beginning.
Okay, the fact that R is...
Well, R is tied to the discount factor.
No, R is the discount rate. R is the discount rate. So beta is 1 over 1 plus R.
Okay.
So beta goes bigger than 1. Little r is going to go negative, and beta will be bigger than 1. Okay. Yeah. So I'm talking about R, and you're wondering what is it? You know, maybe you think about beta. So what we're going to do is the shock is that beta gets bigger all of a sudden. So they think about the future. That's what they want. They're more patient. They want to save. Yeah. It's an infectious patience that's experienced. Everybody has that experience here. So there's a thing here which has been left unspecified, namely the value function. You know, where does that come from? And so that comes from the assumption that there is symmetry here. That is, first of all, the household lives forever, and kind of, you know, the basic parameters are the same. Well, parameters are the same, but variables, of course, are moving around. So as a consequence, it's well known that in this type of environment, the way you get the value function is by iterating on doing dynamic programming. So this value function is defined as the fixed point of this particular dynamic program, where that expectations, as Mick was saying, is a function of the density function is pinned down by theta. Theta will be evolving over time, so we have to do that dynamic programming at lots of different times for different thetas. I've said this, now this is my third time, but that households can map X into the aggregate variables that they need to define their budget constraint. Okay, now, anybody who's worked with recursive representations, there's always something like that. And this is that thing here. But we're in a learning world, so, you know, they're actually kind of smart. So what I'm going to characterize this loosely as, we're assuming that they're really good at static general equilibrium theory. From the perspective of our ultimate conclusion, we didn't anticipate what it would be, this is a conservative assumption. We're going to find that learning has a dramatic impact on the outcomes. And so here we're attributing a lot of ability for these people to do general equilibrium thinking at a static level. However, they are terrible at dynamics. They don't know how. They're not going to know how to think about the future. They're going to use Bayesian stuff to think about the future. There's another thing which I'm surprised no one noticed here. I didn't fully use the Bayesian thing. I should have used theta prime over there, which is the Bayesian priors that they would get after observing X, the posteriors. And we are, for computational tractability, going to pretend when we solve this thing that they know what tomorrow's theta is. We are going to try and fix that. We're not happy about it. We have some experience with doing it the right way, but we're still not sure. And we didn't see a big difference between this and what I'm going to show you. Anyway, so the assumption I'm going to make, which is that in the current period, I'm going to assume that I'm not going to update my priors after observing current X. That's something that Adam and Marcet call not internally rational. And it's especially obvious when you write the problem down in recursive form. I don't think it's going to matter when we do this the right way, but this is what we've done. Okay, production and firms. We have the Dixit-Stiglitz thing that's standard in the New Keynesian model. Final good is created by aggregating by a competitive firm that aggregates intermediate goods, and those goods are produced by monopolists. The intermediate good monopolists have sticky prices like Rottenberg. That was very important for us because the Rottenberg makes things much simpler. The problem, we write it out in recursive form, and I'm not going to show you what it looks like, but it looks almost the same as the household, with the obvious differences. For the firm, its state variable is the price it set in the previous period. It doesn't issue bonds. And the decisions it makes are what is its price going to be. And they have the same belief updating process. Now, all these people, none of these people talk to each other or coordinate. So that's the level at which you have, it's like K-level thinking. In K-level thinking, no one coordinates. But they're all kind of ignorant in the same way, and they're all going to be learning in the same way. Yes?
Just a quick question. Do you have any sense whether the Rottenberg method, like relative to Carroll model, just with Rottenberg, just the quadratic form you make it,
Okay, so of course the answer, we've done Rottenberg and Calvo before in other ways, and we've never found a significant difference. Actually, we're shocked to discover some similarities that we didn't expect were there. The intuition we have, and we've developed a lot of intuition, and I'm going to try to show you some of it. It doesn't ever, it's not different between Calvo and Rottenberg, but we've not done the calculations here. The problem with Calvo is it has a state variable if you want to, do it a serious nonlinear. And but with Rottenberg, as long as you're working with inflation, you don't have a state variable. And the number of state variables, actually now you can see why we care about the number of state variables. We have to do dynamic programming for the household, and we have to do dynamic programming. It's the same kind of dynamic programming problem for the firms, and it has to be done for a bunch of variables, including one variable here, which is a big long vector of 8 things. So the curse of dimensionality is a huge issue here, and so that's why we go.
I'm just thinking like that. When you look at global solution, because Rottenberg has this quadratic form, then it may create another.
Well, but there's a lot of there's a striking amount of similarity. For example, in Rottenberg, there's a maximal amount of inflation that's possible, which you wouldn't maybe not automatically have thought, but although maybe you would, because there's one particular equation that shows that. And then with Rottenberg, you have the same thing. But I agree with you, the convexity, I've seen the convexity in here, and I don't know if the convexity would look exactly the same. Okay, so yeah, so the intermediate good firm solves a dynamic programming problem similar to the household, but I'm not going to show that to you. Fiscal policy. Okay, in the baseline simulation, which I'll start out with, government spending doesn't change. So it's equal to GH. H is used for household, and then it's also for high, I realized just now. So G is equal to the high means when you're out of the zero lower bound. So baseline G is constant. And in the alternative, we have that G is equal to GL. It's higher in the zero lower bound. This is the way we did this stuff in the paper with Sergio. The government's going to use lump sum taxes to balance the budget in each period. And then there's monetary policy that follows the usual Taylor rule with a lower bound on it. Okay, how do we get market clearing well, we have something called a period equilibrium. So it's very much in the spirit of, I always want to say Schmidt, Rohe, and Uribe. Anyway, but it's not. It's in the spirit, very much in the spirit of Woodford. So the way we are going to define a period equilibrium is the following. We're going to move that x around until all labor markets clear, all various equilibrium conditions are satisfied. It's very much inspired by Giuseppe and Preston, who do something very much like that in a learning context. So what we're going to do is we're going to, I think I may have said this here oh no, I didn't. Okay, so what we're going to do is basically, I mean, Guénéry would have put it as, we're going to give the households and the firms clairvoyance in the period. Or put differently, we're going to imagine there's an auctioneer that calls out different values of X and stops when all the markets clear. But so the net effect, though, is that involved in this period equilibrium, there's a huge amount of what you might call rationality by the households and knowledge. They know what the mapping is from X to the aggregate state. By the way, the bottom line here is this turns out to be 2 variables and 2 unknowns. We move X around until the bond market clears and until the prices set by the firms coincide with the price implicit in the second element of x. Okay, so that's how we define a period equilibrium. I'm not going to give you a learning equilibrium because it's kind of obvious. It's just all the value functions, all the decision rules, and such that market's clear. Okay, how do we update beliefs in this model? Well, households and intermediate good firms have the same beliefs about X. So somehow we don't say Y, but they all they have the same theta. And we're going to assume that log X, so the elements of X are log normal. So log X is independently drawn from a normal distribution, but these people are uncertain about the mean and the variance of these variables. We're then going to give them a prior about the mean and the variance, and that prior is going to be normal inverse Wishart. The beauty of normal inverse Wishart is that it's the posterior is also, when the likelihood is normal, the posterior is also normal inverse Wishart. This vector x theta has 8 parameters, so it's a very high dimensional problem. And Bayes' rule has this beautiful recursive form, completely trivial to implement, just wonderful. Now, the way we simulate the model is that we move forward one period, we apply the Bayes' rule to get a new theta prime and run the thing again. Then, then we get something happen in the next period. Then we go to another period, we update the priors, blah, 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 and that's how we simulate the model. So in this analysis, the prior is a state variable. And of course, the first prior you have to worry about is the one, what do people think in the moment of the shock? So now in this model, they're observing something they never saw before. They assigned a 0 probability to it. And so what we find this very interesting. How do people behave when they see something they never saw before? So what we're going to do is we're going to kind of have a big prior variance on the prior. We could also put a smaller one on it. The smaller one, of course, will give us faster convergence, and we're finding slow convergence. So to be conservative, we're going to put the wider one in here. I'll show you that in a second. Here's what I want to say about. Here's kind of an interesting thing, which is that if you put a mean on this prior that's exactly the rational expectations equilibrium, that ain't going to be a learning equilibrium, because what they'll do is they'll learn away, they'll move away from it. I'll explain that more in a minute.
Is that also true when you do the model construction? So if you do that on set?
Well, yes, but from what we've seen, and we're not comfortable. We're not comfortable, so I'm not presenting that stuff. And I hope that that's what we can be doing ultimately. Yeah, the Adam and Marcet's insight, I think, is a very valuable one. So does now we get to, I got the model, now we go into the experiment. So does learning select one of the multiple equilibria? Well, the answer is yes, so I don't want to, well, it's yes, but in an even more interesting way than we were able to say before. So if we make the prior equal to one of the not stable equilibria, so the mean of the prior is the rational expectations, you wander away and go to ours. Yeah, the variance has to be positive. We always have positive variances. Okay. So, and then how quickly does convergence occur? Those are the two questions. So yeah, there's another question I'm not even talking about, which is the steady states. There are multiple steady states, and there's a big literature on that, and all of our results are consistent with the conclusion of that one, which is that only one of those equilibria are stable. So okay, underlearning. Okay, so scenario, economy was in zero inflation up to period zero. Unexpectedly, this shock happens. One problem with rational expectations, you got two equilibria. These are the parameters that are kind of standard, so it won't bother. You get, this is the standard kind of graph. You can derive, you can just calculate. It's very easy to show that you can express the rational expectations equilibrium as the zero of a particular function in the space of inflation in the ZLB. And we have two crossings. And so there are two equilibria, but this equilibrium is stable under learning, and this one is not stable under learning. Even if you give the mean to these guys, if you give the mean to these guys but have positive variance, they actually go over there. We don't have a mathematical proof of that, but we have done simulations of that. So I'm only going to focus on this equilibrium here, and forget the dash line there. And I don't know why there's an A then B, because I put the B in there. Okay, does learning select one of the two equilibria? So this equilibrium here, which we call the good equilibrium, the B, is stable under learning. When the priors are centered on the steady state, either this or that, both converge to that. So if you start from the good ZLB steady state, you actually wander away for a while because you have a positive variance. But then eventually you realize, oh, then you come back. Okay, this is bad ZLB is unstable. These are kind of like priors that we tried that were somewhat less dispersed. And then there are other priors that are much more dispersed. This is net inflation and log consumption, and we work with the more dispersed because that's more conservative. But actually the conclusions are not very sensitive to which we work with. Okay, so here's a key finding here. So G is not changing, R drops. The solid line here is, this is inflation over here. The solid line shows you what happens to inflation in the rational expectations equilibrium. It's going down by a lot. It falls by, minus, you have to multiply this by 4 actually. No, sorry, this is annualized. So there's minus more than 6% deflation. Consumption is falling by something like 8%. And then the real interest rate is going up really high. Now this is like famous result from Eggerson and Woodford. Now, what's happening in the model is that the way we set these priors up, now you may disagree with the way here we can argue, we set the prior so that the mean of the prior was what had happened before. We simply had in effect, the prior simply spread out, but the mean stayed the same. And so what happens is that in the learning equilibrium, inflation hardly moves in the first period. So it's very different from this thing here. And then what happens is that it slowly comes down. Now, of course, comes the question, is it converging to this? Well, it comes down here, and then to your eye, certainly to my eye, it looks like it's converged here. And if you look at period 1000, this is where it is at period 1000. It's like a staggering thing. If you go out to a period like 1 billion or so, it will converge. But this is what we call slow convergence. And of course, from the point of view of the ZLB, the P that we put in there was 0.8. So that means that on average, these ZLBs will last 5 periods. Well, 5 quarters. This is 20 quarters here. We haven't come close to converging. So this thing, the rational expectations model is completely irrelevant from the point of view of thinking about this thing here. Here what we see is consumption. The effect is much less on consumption. Of course, the main reason for that is that it has to do with why it is that in the rational expectations equilibrium everything falls so much. Well, it's fundamentally an downward inflation spiral that's killing this economy. Expected inflation goes down, that makes the real interest rate go up, so people consume more, and then when they consume more, that drives up wages. And sorry, what am I saying? When expected inflation goes up, it means that the real interest rate is, wait, what the hell am I saying? When it's going down. So when expected inflation goes down, the real interest rate is going up, and then consumption goes down, and then inflation goes down. And then when they see inflation going down, they expect it to go down some more. Then it's a kind of a spiral thing. And the firms are the same. If they see low inflation in the future, they're going to want to cut inflation today. By the way, both in Calvo and in Rottenberg. So the spiral in expected inflation is the key to the rational expectations model.
That's the actual inflation.
This is what the inflation in the learning model is.
That's their expected inflation.
Yeah, and no, that's actual inflation. So their beliefs about where inflation is going is only based on past information. So their prior in period zero is the mean of it is that inflation will be zero, but then they're going to see inflation go down a little bit. They respond to that by revising down their expectations.
So expected inflation moves in the same way.
Yeah, it moves in the same way. Yes, yes, yes. And of course, the picture is identical for firms and for households because we're assuming they're the same. They would be interesting to see what would happen if they were different. And then the fall in consumption, because you've deprived the key variable, expected inflation, from affecting the learning guys, because the learning guys only change their beliefs when they see something that makes them think. They have to see inflation lower, then they will have a belief that it's lower. And so now what happens, consumption hardly falls, and of course the real interest rate in the rational expectations equilibrium goes through the roof. That's what made this go down so much. And here we have, and again, we never get convergence. So the impact under learning is small compared to that. By the way, a little footnote here, we have an explanation of the missing deflation puzzle. I mean, there have been many proposals to resolve that puzzle, and there's a sense in which ours lives in that family, because you don't actually start believing inflation falls. No one starts believing inflation until it actually does fall. This is very much like the behavioral thing that Gabex did and other people have done. And learning is very slow. When we use constant gain learning, we get basically the same result, but we don't get the crazy, we don't have the crazy thing by year, after we've gone by, well, I can't divide by, if I divide by 4, I think that's 10. So after 10 years, you more or less converged. But this is a 5-year kind of operation. So I think the right way to infer this is that we get very similar, the results are not sensitive to whether we're using constant gain learning or Bayesian learning. Constant gain learning keeps the gain constant. Bayesian learning makes the gain go down. Yeah.
Could you explain again why inflation does? I'm just trying to work it out in terms of your model. So
yeah.
So you wake up in the morning, suddenly you're very patient, you want to save like crazy.
Yeah.
Consumption drops. And now, so that's a decline in the demand for goods. That's what the firms see responding to, or what? There is a unseeable tiny drop in inflation in the period of the shock.
But we did go to the self-confirming stuff, and the nearly self-fulfilling stuff. I think that's what it is.
Well, expected inflation hasn't changed. It's still centered on 0 in the future, but there's a spread, and then there's an issue. What does spread do in this model? And the answer is not much, because it has the opposite effect on firms than on households. So the spread doesn't, it's basically what's happening in the first period is that people are just reducing their consumption, they're reducing their purchases, but firms, for example, are not particularly expecting inflation to fall. The key thing in the rational expectations equilibrium is that everyone knows in that equilibrium that inflation is going to go down, and it's going to be down at this constant. It's a huge drop in inflation, so everybody wants to start cutting inflation. And I think probably I have like 0 time, I think. What?
You have 5 minutes.
Yeah, so maybe I can just quickly sort of move forward here. Well, here's a slide that explains why these diffusion. A key thing in this model is that what makes priors so persistent is that they're somewhat self-confirming. If I believe not much, if everyone, okay, they're somewhat self-confirming. But there are other, when the monetary authority is busy working too, monetary authority kind of lost its job here. The monetary authority has a very strong Taylor principle. Then if people start thinking there's going to be more inflation, the monetary authority is going to produce lower inflation. And so what we show here, it's clear I'm not going to be able to do that, but what we show in these slides is examples when we're not in the ZLB, then you get somewhat faster convergence. Actually, since we're doing that, I might as well just jump to that, because I think I'm more or less out of time.
No one's allowed until you show the multiplier.
Well, I wanted to show, make this thing. Let's say we do this same shock. I think this is an important lesson. Like, what is it about this environment that's doing this? So one answer is that it's the self-confirming aspect of the inflation when beliefs about inflation when the Fed is not present, or put differently, when the Taylor principle is not present. Now, there's a way of keeping the Taylor principle in the picture by simply ignoring the ZLB. Okay, that's what the dashed line does. So if I ignore the ZLB, the thin line is always rational expectation. So if I ignore the ZLB, then the collapse isn't so great. No big surprise. But the dashed line is learning in the no ZLB, and notice they sort of converge quickly. I mean, you might still be concerned. They only converge after 10 periods. Okay, so, I mean, that's 2 years. Maybe that's a long time. But it's different than 10,000 periods. And same thing here. In the middle graph, you can see consumption looks like the rational expectations equilibrium. And so the Taylor principle has a way of anchoring inflation expectations so that movements in inflation by itself don't... Now, Marty was saying I should do the government spending. So government spending is an example where the critical medium through which government spending has an effect is through expected inflation. So in this picture here, I've got, so the solid line is, this is no increase in government spending. And then this little line here is with the increase in government spending. So what you can see here is that when there's an increase in government spending, you get a big multiplier. It has a big impact on the drop in output, and it has a big impact on the real interest rate, and it's all operating through expected inflation. Okay, now in the case of the learning model, this dashed line and the solid line are kind of roughly the same, which shows you that government spending has very little effect. Why? Well, because the expected inflation is not in there. They just don't know all of this stuff in the learning model. So in the learning model, what happens is that we just get a very small the difference between these two kind of solid, well, this is a solid dashed and this is the solid line. The difference between these two lines is very small, so the multiplier is tiny. And here's a picture of this. So the upper line is the magnificent big multiplier in the rational expectations equilibrium. It's nearly 4, right? It's an insanely large number. And the multiplier in the learning equilibrium is kind of it's less than 1, and then slightly positive eventually. So it's roughly
There is because the agents don't have a way to figure out what G is going to do to C next year.
Exactly. Well, they do.
No, they do. They know what G is doing. No, we're telling them what G is doing.
Well, they know what the G is. They don't know what it's going to do.
Yeah, to see.
No, wait. No, hold it. They know for sure what G is as a function of R. And R is stochastic, and they have the correct belief about the stochasticity of R. So they know exactly what G does in the same way that it's known in the rational expectations equilibrium. They know what G is doing.
How do I update my C for next period? And then I get C for next period.
That's the inverse Weierstrass distribution.
Yeah, based on looking at the
whole point is they don't know the dynamic effects. They have to learn it.
Yeah, they have to learn it. Yeah. Okay, so how many hours do I have left? Oh, 0. Okay, so let's go to the conclusion here. Oh my God, see, I got this example here. So I'm not going to talk about this, but this example would let you work this out in your hotel room. The fact here it takes 1 billion years to converge. Okay, and it's a famous example from 1986. All right, so conclusion, we consider a particular setting, the ZLB. That's very important because the Taylor principle has been abolished, which seemed to lack, although we didn't know that in advance that would be important, which seemed to lack much precedent. We found the learning might take so long to happen. Oh, this is an old draft. Sorry, I changed this. We found the learning might take so long to happen that the analysis, the rational expectation would actually be totally useless. I mean, the idea of the multiplier is just totally wrong. Now, it may be actively misleading because one of the things that I didn't show you is, well, first of all, because you might think the multiplier is large, that government spending is effective, but there's another a massive thing that's hiding in this analysis, which is in the learning equilibrium, you don't hit the 0 lower bound right away. Okay, so we tried another policy, which is the central bank pushes the interest rate to 0 the minute it's going down. So that requires that the central bank knows what it's doing. Pushes it to 0, and by God, you get approximately the efficient allocations. The efficient allocations in this model are no inflation, no change in consumption, and no change in the real interest rate. By pushing that down, while you still have firepower, so you can still move it down, you push it down to 0 right away, and you get approximately the first bet. So you get something much better than anyone ever dreamed you could get, for example, from the multiplier from government spending. So the learning offers interesting opportunities. Okay, sorry.
Does that mean gradualism is a mistake?
Well, it depends. If you're in normal times, for all the normal reasons, it might be fine. But if you really think, oh my God, there's going to be a discount rate shock, and this is my last chance to counteract it, then gradualism would be a huge mistake, which is, of course, what Bernanke was.
Well, it could be that's because there's evidence that it was not binding. I mean, some people argue it's super binding, the 0 lower bound, but when we did an analysis of this, we found it was kind of not sort of marginally binding. That's what would happen under the optimal. And Bernanke moved that interest rate down to 0, not instantly, but pretty damn fast, early 2009. This would argue that if he had done it on September 16th, 2008, we could have had the first best, no perturbation in anything.
One way to interpret the results is you don't get a very big multiplier, but you don't need it because the zero lower bound doesn't have as much of a negative impact in the learning model as in the rational expectations model. So we don't worry too much.
You don't need it, but actually that fall is sort of big. I mean, so you still get a 3% or something fall in consumption. So, and the efficient thing is to ignore the discount rate shock in the stat model. This is a function of the fact that we have no endogenous state variables, and the efficient thing is to ignore that. Of course, you get a proxy. I've never seen big difference in open economy, yes, but not in closed economy. I've never seen anything that you don't see in this simple model, unless you're talking about financial frictions or something like that.
Okay. Thank you very much, Larry.